It's a pleasure to be here and talk about the work that has been ongoing. And I'll be talking to you a little bit about the evolution of what we're trying to look at is alternative aerosol materials and the evolution of them, some aging studies we've done, and how we're starting to learn more, but also starting to see a lot of things we don't understand well. So when it comes to these alternative materials, I just sort of want to give a little bit of sort of the way I look at them. And that is, there's the bulk, and we've heard Rajan was talking about sort of bulk properties. And the bulk properties of the aerosol are important for the radiative forcing, they're important for scattering. This question of what the direct versus diffuse light does, which we haven't talked much about, but the paper that was just quoted by Graham Feingold is really about that, the implications of the diffuse light. And that implicates things like stratospheric heating and other effects. That's the bulk. And I would say generally, the bulk, we use ideal materials, and I'll show how the actual materials may not match that. And Rajan was showing how there's misassumptions about the bulk materials, but it's still somewhat easier to understand the bulk of a material. And then there's the surface of the material, and that is unfortunately also important. And as I think some people were mentioning, I think John Abbott was sort of talking about how knowing what the surface is and doing studies in the lab where you have organic coatings on the surface, these things are really challenging. The surface is really what is that layer of molecules on the outside, and if you're in the lab, how do you know that that layer of molecules on the outside is the same as it is in the stratosphere? So the surface, unfortunately, is important for heterogeneous chemistry, which is tied to ozone, but also many other things that are important. It's important for ice nucleation, most likely, as John was talking about, and I'll also show the diamond studies again. And I think it also plays a role for coagulation, probably really only in the sense that I think if you're able to have charges on them, that can suppress coagulation. And if you don't have charges, fundamentally, it means when they hit, they probably stick with each other. But the surface, unfortunately, also matters. That is a much harder problem than the bulk. But even so, the bulk requires quite a bit of study as well for these materials. So the questions that I'm going to be talking about here and extend from November is, how do the properties of commercial particles actually compare to these textbook values we use? And Rajan was showing how the alumina, for example, doesn't really match what you get from the textbook studies if you really look at it, and I'll sort of extend that in other directions. And we're also going to look explicitly at how optical properties and chemical composition overall in simulated lab experiments, similar to what Markus Ammann was briefly talking about, where you expose things to HCl and UV in this case for these things. The last thing I want to say about the strategy for these alternative materials, the idea is, of course, the only reason to study them is that you think you can reduce risks of some form, all right? And that is stratospheric heat in the stratosphere, which are things like stratospheric heating, perhaps ozone, and they don't add, the other important caveat is they don't add significant risk in the troposphere. And so one of the things that we've been looking at, and I'll actually say diamond is a little bit of an outlier, it's sort of more of an idealized case study of what an ideal material could be and whether it exists, is to really use earth-abundant materials, because at least then down here there shouldn't be as many surprises if we use materials that are abundant in the atmosphere, sort of as mineral dust, as all kinds of forms. There shouldn't be. We still don't know what it's in the stratosphere. That is new, and we've got to be careful about that. I'll explicitly say that we're actually not looking at those stratospheric impacts, but that our choices are in part driven by that. That's the point. We're also not looking at things, the cost of these ideal particles at the moment, which Faye's group has also been showing things, can you actually get monodispersed things of these? We haven't looked at those, and just to be clear. I want to say one more thing about ozone. There's a lot of focus on ozone and what stratospheric aerosol injection does to ozone. And I want to be careful to not sound too heretical, especially as Jim Anderson has his office next to me, and I have to be very careful what I say. There's two things I want to point out. One is that I think for sulfuric acid, the stratospheric ozone fears about SAI, whenever it would happen, 2040 or something like that, are actually probably overemphasized compared to other aspects like stratospheric heating. I also want to show with this figure, which is, this is work that Deborah Weisenstein did a long time ago with the AR2D model. It's not like a very sophisticated model. But what it actually shows you is that also this idea that more aerosol is always bad for ozone or less aerosol is worse is actually quite interesting in this model. If you look at this in 2040, the x-axis is sulfuric acid surface area density, and this is the global ozone column change relative to this point over here, which is roughly what the background sulfuric acid concentration is. You can actually see that, of course, in 2040, when you start increasing it, you see this trade-off that then people talk about for radiate forcing versus ozone, and you see sort of column changes at these are really quite large sulfuric acid amounts in the stratosphere. You know, it's like 6% or something like that in that range. I'm not saying that doesn't matter, but I would argue it's things we've seen and are less. Why is that so much less than in the year 2000? And that's because there, of course, we hope is less inorganic chlorine in the stratosphere. So as we're going in the future, right, the actual ozone impacts are getting less and less from sulfuric acid. The other thing that you can see that's interesting as well is ozone actually also gets lower if you go to less sulfuric acid aerosol in the stratosphere. So it's not like actually an atmosphere without sulfuric acid in the stratosphere would have lower ozone. All right, and that's because of N2O5 primarily. So just to be clear, we've got to be careful when we worry about this. For stratospheric heating, I'm going to show a bunch of things. This shows an old spectrum, what doesn't really matter. What you see here is that the part that we're going to focus on is the infrared, in contrast to what Rajan was showing. We're looking at terrestrial infrared and really sort of defining the atmospheric window that we care about sort of being roughly between 800 wave numbers to 1400 wave numbers. And if we have absorptions in there, then they can effectively absorb terrestrial infrared and heat up the stratosphere. And if they have absorptions out of that, it is not as important. And so that's sort of what we're going to look at. Obviously, you don't really want solar absorption as well. Here's the particles we've investigated. We've looked at 4 different types of diamonds that you can buy. They are made in different ways. They're done by detonation, polycrystalline, high pressure, high carbon. They have different sizes normally when you buy these from the manufacturer. We have looked, I won't talk about this, alpha alumina. The alpha alumina, the size range, we investigated this by X-ray diffraction, confirming that it's primarily alpha alumina, little delta in there. The IR properties actually match the textbook spectra very well. I won't talk about that. We've looked at calcite. I talked about that in November. The IR properties also match. We started to look at a range of different carbonates. These are all carbonates that occur naturally. That's why we chose these. Why are we looking at different carbonates? What I follow here, I'm actually this semester giving the introductory chemistry lecture for close to 400 students. And I talk about this here, KSP. Anyway, what is KSP? Anybody know here? Solubility in water. Why am I talking about that? It's because in the end, if you have species that even dissolve in the environment and could even dissolve in rain droplets, to me that's sort of a nicer solution. It also means they should dissolve, let's say, if you had to inhale them. They have various degrees of solubility. And what you can see, what that's interesting is that magnesium carbonate, this means it's the most soluble of these compounds. It's also known from, in essence, introductory chemistry, that interestingly enough, magnesium carbonate has very low reactivity with aqueous HCl, not gas phase, and calcium carbonate has higher. So by choosing different carbonates, we can start looking at sort of a modeler between how soluble it is and how reactive it may be with HCl. Ideally, we want it not to be reactive with HCl because the chemistry gets complicated. And the other thing, of course, is we're also looking at dolomite, which is sort of in between. These are all very earth-abundant. We have huge amounts of wind-blown dolomite mineral dust, for example, in the atmosphere. So let's start with diamond. We have these 4 diamonds, and then if you think of a diamond, it looks like a nice crystal or something like that, or a cut gemstone. When we look at the actual artificial materials we get, we first confirm, are they diamond? We do X-ray diffraction that tells you about structure. And the first striking thing you find from these 4 different materials is that, yes, they are all diamond. They match with the diffraction lines, the angles. You see the diffractions are at the right angles. This tells you it's the right structure. It is diamond. But you can see, as I showed in November, that some of these have very sort of low-intensity broad lines. And that tells you that they are not nice single crystals of diamond. They're actually polycrystalline material. And from the width of the bands, David Werber, the grad student in my group who's here, was able to determine that the individual crystal domain size is 4.5 nanometer or smaller for these detonation-made diamonds, and it's significantly bigger, 30 nanometers or larger, for the ones that are made in a different way. That tells you these are really quite different types of materials. The way they're put together is different, and we'll see how that matters in a little bit. If you look at this is what SEM image, this is an AFM image, and that my postdoc Aisha was also here took, and David took the SEM image of the diamond. This is the detonation one. And you can see they say it's 100 nanometers, and you can see these little units that are all stuck together here, that the individual units are perhaps around 100 nanometer. And if we do dynamic light scattering and give it time with ultrasonica to really get apart, they are 100 nanometers, so they actually give us the right information. But when we try to make them and deposit them, they're always agglomerates, right? And down here you can see the Thermo Fisher particles, which actually are more individual still. They're not quite as clumped together, but you can see how irregular these shapes are. Right, that makes life much more complicated. And these are actually, which they also say, they are larger. You can see that they're half a micron or larger in one dimension, and perhaps a few hundred nanometers in the different one. So very irregular shapes. All right. So this makes also life more difficult to actually model their interactions. Then not surprisingly, we've done aging experiments where we expose them to HCl and even UV and diamond over simulating a year time scale when we're doing this by having a higher HCl concentration, which is not exactly the same, but good enough. Not surprisingly, diamond does not react. But fundamentally what we find is it's not changing shape. The HCl doesn't change it. We also don't see chlorine embedded in the diamond. It's unreactive, not too surprising. Even under UV, we don't see a bulk change in this material. That doesn't mean that the actual surface couldn't be changing in some way. We don't see this with these methods. This makes modeling the properties challenging, the shape of this. Now, let's look at the infrared properties of these diamonds. What you see here is from the Journal of Functional Diamonds. It's interesting that there's a whole journal dedicated to this. I showed this last time, that the infrared and it just shows you that industrial production of diamonds is really important, right? There's a lot of this. It actually shows you that in the infrared, this is the atmospheric window, the green box, that there are diamonds that have no absorption here. These are really ideal in infrared. These are type 2 diamonds, which are rare in nature. And then you can see all these other ones can have quite significant bands. We don't know the absolute magnitude here, but there can be significant bands, and those come from nitrogen or boron defects in the lattice. So Aisha, my postdoc, took FTIR ATR spectra of these materials. And when I was here last time, we didn't have those because I'm stupid. Because there's a window that you do this on. You put the material on this. Turns out that what we were using was made of diamond, and we put diamond on top of that. And my postdoc was trying to tell me she didn't think this was a good idea. I was like, why? Just do the experiments. It didn't work, and she was right. Anyway, we got a germanium window, so we can do this now. And what you can see here is quite interesting that in this atmospheric window, these are different types of diamond. We see, again, significant structures in here, but they actually aren't these defect structures. And looking at spectra that are out there, they mat what people sort of call graphite oxide, which is an ill-defined compound, fundamentally graphite that slowly gets oxidized. And so this probably comes from inclusions in the diamond, from the making of it, sort of graphite-like traces of it, and they just absorb a little bit. They're still quite small in absolute values, but they vary quite a lot. So here again, the commercial material that we have, at least mainly so far, deviates, similar to what Rajan was saying, it deviates from these nice textbook properties also in the infrared. I'll briefly talk about the fact that we can also measure the optical properties of individual materials, not as sort of what I just showed you was a whole bunch of particles. One of the things we're interested in is a deviation in the particle-to-particle properties that we're getting from manufacturers. I won't say too much. It's a complicated method, but what you can do, it's scanning near-field optical imaging. You can get the topography, you can sort of get the size and the shape of a particle. At the same time, you can measure the complex refractive index of this in the infrared for everything. And what I'll just say is that what we know from this, I did some work on this as well. These maps are too complicated. I'm not going to talk about them. Is that diamond has very low absorption in infrared, lower than silicon. It sort of matches what we sort of think. The most important thing, again, is that here we also show that after the long-term HCl exposure, the properties actually don't change. So what we're seeing with diamond is that we can say exposure to HCl and UV doesn't change the bulk properties, right? Gaseous HCl. This is not liquid HCl, right? This is trying to simulate it's in nitrogen. Yeah, that it does not appear to change the bulk properties of diamond. I don't know. And then we did these isonucleation experiments I showed last time. But as a new people here, I want to show this. KIT, our collaborators at KIT, did some very nice work putting the diamond into the AIDA chamber. What you can see here is a whole range of different experiments. We have two types. We have the Thermo Fisher diamond, which is a little bit larger, but purer, sort of more textbook-like. And we have the one of the detonation diamonds. That's the one that's called AE. Tells you the number density we had in here. We also did experiments where we had them pure, and then we had them where we involved them in coating with sulfuric acid to look at whether this does a deactivation of the isonucleation properties. And if you look at the sizes here, I'll show a little bit more. I decided to add this because we've been talking about how do you disperse these particles, that the from dynamic light scattering, the actual size of individual particles we get for this one kind is 185 nanometers. What we see in the chamber is around 400, and for the detonation one, where the dynamic light scattering says they're actually 100 nanometers, the size distribution we get is around 450. I'll show that here. What you actually can see is that it's a multimodal. This is sort of trying to pick up on, we saw in the talks that was, I think Simone was showing, like, if you put diamond in, you get all these different fractal modes, you know, tetramers. And you can sort of see that this actually is multimodal. This is our size distribution. It's done with a powder disperser at the KIT chamber. And, you know, you have one dominant mode, and really not much above that, about 450 nanometers. This is the detonation diamond. But you can see that there are also sort of these smaller agglomerates as well, right? So we didn't size select the size we're doing for the isonucleation experiments. This is all inside the chamber, being measured inside the KIT AIDA chamber. But you can see there's sort of multiple modes. What we see as a net effect is, again, we've seen a little bit of this before. We have different temperatures. And this is the supersaturation with respect to ice, at which you start seeing freezing. The blue dots that I show you are for bismuth triiodide, which is generally assumed to be a fairly good ice nucleus. And now comes the diamond. This is the detonation diamond. And you can see that it is arguably, I would say, a very good ice nucleus. We get isonucleation at really quite low ice supersaturations. And if we look at that now, that was the detonation diamond in the top. If we look at the other diamond without coating, which are the orange squares. So orange means no sulfuric acid coating, all right? And so what we can see here is we repeat the experiments, we fill them in, that they are fairly similar to different types of diamond. Within uncertainty, they're the same. So whether we take the pure one, the slightly larger one, the detonation, the non-detonation, they are actually both, at least I found them surprisingly good ice nuclei. You can also see that sulfuric acid coating, these are the blue ones. You look at the blue squares compared to the orange squares, that's for the Thermo Fisher diamond. You can see that that gets significantly deactivated versus the detonation one that we used, where there's really, within uncertainty, no deactivation effect, all right? And so that's quite interesting and shows you the complexity. You have these commercial materials, and they can behave in some ways similar and in some ways quite different. And that really poses a challenge, I would say, and needs a lot more understanding of what's going on. And actually, from last time talking to people, it seems like this likely could be also this porous, what John was talking about were these intentionally made materials that have porous isonucleation. It is possible that these get that anyway because they're so fractal inside of this at a very small scale that perhaps in some ways they can also act as pores that make it easier to get isonucleation. But that is speculation at the moment. But it shows you the complexity of the diamond, and that going from this ideal world of putting ideal diamonds in a model to looking at real diamonds is a really big step. I'm now going to look at the different carbonates, and that is some work I want to go on. And the reason we're looking at the carbonates, why are we looking at that? There's this earth abundance aspect that's important. The other part is if we look again at the infrared spectrum, these are, in a sense, textbook spectra, but these are actual materials. These are not pure materials. These are materials that were naturally occurring. And you can see that they have some absorption in the atmospheric window. You see a few bands and a growing band in here, but it's quite low. And that is the kind of material that with that, you get a little bit of stratospheric warming in the model, but not a very large degree. And they all look kind of similar, right? So the carbonates, the infrared is dominated by the same modes. And now, we wanted to look at these materials, again, now we go from this and say commercial powder material that you can get. We already looked at calcite, I showed last time, it matches. The interesting thing is dolomite and magnesite, so these two, there you get a great match, and then we got commercial zinc carbonate, and this was from a chemical supplier, VWR or something, and said it's zinc carbonate, and that one, as I'll show, it does not match at all, but it's actually a different compound. It's a basic zinc carbonate, so in a sense there's zinc carbonate in there, but the fact that it has these OH groups really changes chemistry, as we'll see. So here is a comparison. One of the reasons to go after zinc carbonate is that it's less reactive than calcium carbonate, and you can just see this. You know, could be another introductory chemistry experiment. You're gonna add HCl just to these are the actual powders we're using, and you add this, and they both bubble a little bit, but the calcium carbonate, you see a lot more bubbling going on, and even after one, nearly all the calcium carbonate is gone. Even this not zinc carbonate is actually reacting already slower than the calcium carbonate, right? It's known, for example, that magnesium. Yes, it's not all, right, it's reacting in a different way. It's not making as much CO2 because of that. So this is, and initially when we did this, we actually thought, oh, that's because zinc carbonate reacts more slowly, but actually it's just not. And the other thing we noticed also, you get some calcium carbonate, which looks like a nice white powder, and you start putting HCl into it, and it turns bright yellow, and I think there's impurities of iron in it. The morphology, if we now do this and expose it to gas phase again, and UV, the HCl reaction that occurs there, and we know this occurs also from work that Sandro and Marcus and others have done, the gas phase HCl does react with calcium carbonate, but if you sort of just compare the overall what it looks like, you don't really see, after even a sort of exposing it to like a year equivalent, you don't really see big changes in the morphology. It's sort of not melting, or you see a lot more cracks, which is actually a little surprising. For zinc carbonate, same thing, and again, this is not zinc carbonate, same thing, we don't really see that. But if we look at the chemical composition in a little bit more detail, these are just EDS spectra. So here we can see the calcium peak in the EDS spectrum, and if we just expose it to HCl, sort of a long duration experiment, you start seeing a small chlorine peak, and this is only semi-quantitative, but relatively speaking, compare it. The calcium to chlorine ratio is about 100 to 1, so it's still only a little bit reacted, and that is consistent with the fact that we don't see sort of large morphological changes. When we add UV, we see for the calcium carbonate a significant increase in the reaction where the ratio has changed significantly. And this is not just for calcium carbonate. We see the same effect with our hydrozincite plus HCl, where initially the ratio, if we do sort of without, not initially, if we do it without UV, as we just said, it looked like it reacts slower. The zinc to chlorine ratio is much higher, but it actually changes it a lot when you expose it to UV again. And I actually have no clue why this would be happening. I don't understand how UV would change so bad. I hope that people here are able to help us with this. I just want to point out, you see a little bit of a copper peak sometimes, and that's because all of these are on a copper substrates, and sometimes the electron beam penetrates through to the copper for that. All right. Last thing I want to show is that these things, we're getting chlorine into these compounds. But again, the bulk properties, this is now showing the infrared spectra, how they change for calcium carbonate, aging with HCl and UV. We know from IDS HCl is going in, but we don't see, here's our infrared spectrum, and this is for either fresh or aged calcium carbonate, and there's really not a significant change in the spectrum. We see a narrowing of this band from the unaged, but we don't see the calcium chloride band, which is quite clear, which is sort of sitting right around here. It's really hard to say quantitatively anything is happening there. So we don't really see a big change. Again, the bulk properties appear to be conserved. For the hydrozincite, we can actually see, again, back here are sort of the ones we worry about for the atmospheric window. I'll get back to those in 1 second before I wrap up. You can see at a different band, you can see this band, which is known to be zinc chloride. It is showing up here. Again, the other ones down here, in the previous one, I think they're just too small to see within the changes of the other bands. The reason we actually also know that this is not zinc carbonate is because there's a literature spectrum for hydrozincite, and that matches perfectly with our spectrum and not with a zinc carbonate, right? So, conclusions are, for the optical properties, I think measuring the bulk, understanding the bulk, it can be challenging, there's a lot to do, but those I think we can really go after and figure out what is an ideal material and how much do the actual materials you can purchase match what you get, right? So I think that one, there's good reason to make progress in that. The complex shapes, what we're learning, I think, is that these complex shapes for these materials and the question how well you can actually disperse them do pose some challenges if you say you want to actually quantify the effect of if you were putting out a certain amount of these particles. I think that it really is a significant challenge. There are materials that don't seem to photochemically age, like diamond and alumina. The carbonates do react. What we need to do is we want to do more evaluation of these less reactive carbonates, because for me, a carbonate that's less reactive could be a very interesting choice if it has the same optical properties. I have avoided the studies of heterogeneous chemistry. We're restarting those soon. Our mass spectrometer broke, and I had to buy a new mass spectrometer. And as Simons may have noticed, I didn't ask for funding, but I've managed to find the funding for that, and we're getting a new mass spectrometer in the near future. And then we're going to continue the heterogeneous chemistry studies that we previously had done, for example, on calcium carbonate. We really need to quantify the optical properties. What I've shown you so far was all qualitative. What we need are quantitative values to put them into models, right? And that's one of the next steps. We're going to do additional isonucleation property studies together with the KIT team of other diamonds and carbonates. And again, we actually really should be giving these to other people as well. And I'll leave it at that. Thank you.